Imagine a world where ice can burn your skin, water boils without heat, and metals change structure simply because pressure rises. These strange effects are not science fiction. They are consequences of how pressure and heat shape the phases of matter, quietly controlling everything from clouds in the sky to magma beneath Earth's crust. Welcome to Mattermosaic, piecing together the universe, one discovery at a time. Today we explore how pressure, heat, and phase changes interact, revealing the hidden physics behind solids, liquids, gases, and the transitions that connect them. Long before modern thermodynamics existed, early civilizations observed phase changes without fully understanding them. Ancient Greek philosophers like Aristotle described evaporation and condensation qualitatively around the 4th century BCE, but precise measurement began much later. In the 17th century, Galileo Galilei's thermoscope allowed scientists to track temperature changes, while Evangelista Torricelli's barometer experiments in 1643 demonstrated atmospheric pressure. These tools made it possible to link heat, pressure, and matter's changing states quantitatively. Temperature measures the average kinetic energy of particles. Pressure reflects how frequently and forcefully those particles collide with surfaces or with each other. Together, they determine the phase of matter. At low temperatures, particles move slowly and arrange into ordered solids. With added heat, motion increases, allowing particles to flow as liquids. Further heating breaks intermolecular attractions, producing gases where particles move independently. This relationship became clearer during the 18th and 19th centuries. Joseph Black, working in Scotland in the 1760s, discovered latent heat while studying ice melting. He realized that temperature could remain constant during melting, even as heat energy entered the system. This energy was not raising temperature, but breaking intermolecular bonds, enabling the phase change. Black's work laid the foundation for thermodynamics and industrial steam technology. Pressure adds another dimension. Increasing pressure pushes particles closer together, sometimes forcing gases into liquids or solids, even without cooling. Conversely, reducing pressure allows liquids to boil at lower temperatures. This effect explains why water boils around 90 degrees Celsius at high mountain elevations rather than 100 degrees at sea level. The underlying principle involves vapor pressure, the tendency of molecules to escape a liquid's surface. Boiling occurs when vapor pressure equals surrounding atmospheric pressure. By the 19th century, scientists sought comprehensive models. Benoit Paul-Émile Clapeyron in 1834 mathematically described phase boundaries, later refined by Rudolf Clausius. Their equation relates pressure, temperature, and latent heat during phase transitions. This Clapeyron-Clausius relation remains central to meteorology, climate science, and engineering. A powerful way to visualize phase relationships is the phase diagram. These diagrams map temperature versus pressure to show where solids, liquids, and gases exist. One famous example involves water. At standard atmospheric pressure, ice melts at 0 degrees Celsius and water boils at 100 degrees Celsius. But change the pressure and those points shift. Deep beneath glaciers, intense pressure lowers the melting point of ice slightly, aiding glacier flow. In contrast, inside pressure cookers, increased pressure raises boiling temperature, allowing food to cook faster. Some phase diagrams include a remarkable location known as the triple point. At this exact combination of temperature and pressure, all three phases coexist in equilibrium. For water, the triple point occurs at 0.01 degrees Celsius and about 611 pascals. Scientists use this precise condition to calibrate thermometers because it is highly reproducible. Beyond the triple point lies another boundary called the critical point. First identified experimentally by Thomas Andrews in 1869 while studying carbon dioxide in Belfast, Northern Ireland. This point marks where liquid and gas phases become indistinguishable. Above the critical temperature and pressure, a substance becomes a supercritical fluid, exhibiting properties of both liquid and gas. Supercritical carbon dioxide is widely used today in food processing, decaffeination of coffee, and green chemistry extraction methods. Phase changes also shape Earth's climate system. Water evaporation from oceans absorbs heat, while condensation in clouds releases it. This transfer drives atmospheric circulation. Hurricanes, monsoons, and global weather patterns all depend partly on latent heat exchange. Understanding these processes has been essential for modern meteorology and climate modeling. Inside Earth, pressure and heat determine geological transformations. Minerals change crystal structures under extreme conditions. Graphite converts into diamond at pressures exceeding roughly 5 gigapascals, combined with temperatures above about 1200 degrees Celsius, conditions found deep within Earth's mantle. These phase transitions record geological history and help scientists infer conditions inside the planet. Phase changes are not limited to classical states. Plasma, often called the fourth state of matter, forms when gases are heated so intensely that electrons separate from atoms. This occurs naturally in stars, lightning, and auroras. Laboratory plasmas enable technologies ranging from fluorescent lighting to experimental nuclear fusion. Here again, heat and pressure define the transition boundaries. Modern physics reveals even more exotic phases. Superconductors emerge at low temperatures where electrical resistance vanishes. Superfluids flow without viscosity, near absolute zero. Bose-Einstein condensates, first produced experimentally in 1995 by Eric Cornell and Carl Wyman in Colorado, show atoms merging into a single quantum state. These discoveries extend phase transition science into the quantum realm. Industrial technology relies heavily on controlling pressure and temperature. Refrigeration cycles use compression and expansion of gases to transfer heat efficiently. Power plants convert water into high-pressure steam to drive turbines. Metallurgy carefully manages heating and cooling rates to produce desired material properties. Even food preservation uses phase control through freezing, drying, and pasteurization. In space exploration, phase behavior becomes critical. Liquid hydrogen and oxygen fuels must remain stable under controlled pressures and temperatures. Mars exploration missions study carbon dioxide frost cycles at polar caps. Planetary atmospheres, from Venus's dense superheated gases to Titan's methane lakes, illustrate how different pressure-temperature combinations produce entirely different environmental conditions. At a fundamental level, phase changes reflect competition between energy and order. Heat introduces disorder by increasing particle motion. Pressure often promotes order by forcing particles closer together. The balance between these influences determines whether matter crystallizes, melts, evaporates, or transforms into something entirely new. Theoretical advances continue. Statistical mechanics, developed by Ludwig Boltzmann in the late 19th century and expanded through 20th century physics, explains phase transitions using probability and particle interactions. Modern computational simulations model phase changes at atomic scales, improving materials science, nanotechnology, and climate forecasting. These insights remind us that familiar experiences like boiling water or melting ice represent profound physical principles. Everyday observations connect directly to deep laws governing energy, entropy, and molecular interaction. Phase transitions serve as visible expressions of invisible microscopic dynamics. Pressure and heat also shape biological systems. Cellular membranes rely on temperature-sensitive phase behavior of lipids. Protein folding depends on thermodynamic stability. Extremophile organisms thrive near hydrothermal vents, where pressure and temperature would destroy most life. Understanding these limits informs biotechnology and astrobiology research. Even the search for extraterrestrial life considers phase diagrams. Liquid water requires specific pressure-temperature conditions. Mars, Europa, Enceladus, and exoplanets are evaluated partly by whether those conditions exist. Phase science thus guides one of humanity's most profound scientific questions. Reflecting on all this, pressure and heat emerge not merely as physical variables, but as universal sculptors of matter. They dictate whether clouds form, metals strengthen, fuels ignite, or planets develop habitable environments. Phase transitions connect laboratory physics, planetary science, engineering, biology, and cosmology into one continuous story. Understanding these processes deepens our appreciation of nature's unity. The same thermodynamic laws govern boiling tea, volcanic eruptions, atmospheric storms, and stellar interiors. Phase changes are not isolated phenomena. They are expressions of universal energy balance. Matter does not simply exist in fixed states. It continually negotiates between structure and motion, stability and transformation. Pressure and heat guide that negotiation, shaping the physical world at every scale. This is Mattermosaic, piecing together the universe, one discovery at a time. If exploring how pressure, heat, and phase changes shape everything from weather to planets expanded your perspective, share this with someone curious about hidden physics. Tell us what scientific process you want to uncover next, and subscribe for more weekly journeys across the fabric of reality.